Buonasera a tutti. J'ai le plaisir et l'honneur de vous souhaiter la bienvenue à l'Université de Genève.
Thank you. My name is Norberto. I'm really glad you are here.
But thank you, it was wonderful. I really am, I'm bind here because following such amazing presentation, it's definitely hard. It's me. It's definitely hard for me now to try and come up with something as interesting. The theme of the presentation, the theme of tonight's conference is the future, and science and future. Science, research, future, they're all connected, and hopefully with my presentation, which is really a video that I will show you, I will try to make a connection between research, space research, and future. Perfect. So, this is a standard video that I always show anytime I have conferences, so you're not very special tonight. However, I will try to make the content specific for tonight. I have the honor of talking to young students, and students are my favorite public, always. And the reason is that I'm talking directly to the future right now. You are the future. I have 2 young daughters. They are also the future. And you have something that even the most accomplished person in the world right now, just go ahead and pause it. He has something right now that the most accomplished person, the most accomplished scientists, engineers, and astrophysics or astronauts, is something we all envy that we don't have anymore. You have time. Your time is incredibly valuable, and it's all in the future. That's why it's so important. However, like I always tell my daughters, the future doesn't belong to you. It's not for you to do whatever you want. It's in your hands, however, so it's a great responsibility. I really feel this responsibility when I talk to students, and so tonight I would like to maybe pass a little bit of one word that I bring with me every time I talk to students, and that word is inspiration. The inspiration tonight comes from this video, so go ahead and start. It's the story of my expedition, and I will ask Norberto to pause it every now and then so that I can pick up on the main theme, which is the future. So what we were looking here is a piece of future already. It's a rocket. And when I say it's a piece of future, it's because right now, while it's standing, while it's been erected in Kazakhstan, this is the Cosmodrome of Baikonur in Kazakhstan. Right now, it's just a piece of metal, but it has the potential to bring humans in space. So the future, it's all in the happening. I'm going to turn this around and talk from here. Much better. So in this video, you're going to see the launch. This is the Soyuz rocket TMA-09M, which is the one that I flew in. Right now, there are 3 humans. Let's see if I ever. There are 3 humans sitting up here, about 70 meters from the ground. They're thinking about their future. How long is it going to be? Maybe 30 seconds. Hopefully not. But then you have this vibration coming from below. The rocket, the spacecraft comes alive. And when I say alive, it's like a beast. It's a humongous beast breathing and shaking. And it dwarfs you. And it squashes you into your seat with an acceleration about 4 Gs, 4 times your weight. And in 8 minutes and 48 seconds, it takes you from 0 to 250 kilometers, the same altitude of the comet chaser, and from 0 to 28,000 kilometers an hour, 17,500 miles an hour. And then 6 hours later, you are ready to join the space station after 4 orbits, And there it is. This is the space station. This is the screen that we have in our computer. Now, if you want to pause it for a second, when you see that screen, it doesn't look very futuristic, does it? So we are talking about research in future, but that screen doesn't look very futuristic. Well, there is a reason for that. When you are in space, we use technology that needs to keep us alive. And so we like the technology to be very solid. We don't like to use technology that needs to be tested for something that we are going to use. We like to test technology that you are going to use. Not because we don't want it to work. We want it to work really well. But we test the technology of the future. How many among you are engineers here? So there's a few engineers. How many of you want to be astronauts? There is one, good. You have way too much hair to be an astronaut. But your helmet won't fit. So in 20 years, we will go back to the moon, probably. And hopefully in about 30 years, I hope, we will go even further to Mars. Now, the technology that we are testing today, by that time, will become very solid. That is the principle of test flying and experimentation. So today, on the space station, we use equipment that to you look like the panel on Darth Vader's costume, with the big buttons and the lights. And it's like that because it's technology that comes from 20 years ago or 30 years ago. When I was a kid, I was even younger than you are now. But the technology that we are testing today, oh, that one, it looks like the future. But in 30 years, it may look old to you, but I will remember how new it was to me. But when you land on the moon and on Mars, that's when you will use it, and it will be solid, it will be experimented, it will be tested. It will be yours to use. Let's go back to my old horse here, to the Soyuz. Go ahead and start the video again. Just to give you an example of how old this technology is, this is a periscope. And when I say a periscope, I mean a piece of lens that moves with a little mechanical motor. And that's what we use right here to check our target. We use a radar. These are radars, very basic radars, that let us connect to the space station. Now imagine 20 years ago when we were flying on Mars, and when we were building the space station 15 years ago, those radars were very innovative. So technology has a strange way of being in the past and in the future at the same time. That's the window from which I would be looking outside if I weren't looking straight ahead to make sure that we were hitting the right target. We didn't want to land like Philae. We wanted to land only once. Here, the entry into the space station is always fantastic. It's an amazing experience. Amalia said that they studied 10 years so that they could land and use those 62 hours on the comet. Well, I waited 33 years from the first time that I said I wanted to be an astronaut. I was about 3 years old, and I was 36 when I entered, so I waited longer. This is my crew. You see, this is crew 36 with my colleagues from all over the world, very international crew. We had 3 Russians, 2 Americans, 1 Italian, and then later on we had also a Japanese, so a very international crew. The beauty of the space station, and this is also something that to me belongs to the future, is that it's incredibly international and everybody works with the same objective, and it's something that I hope for the world also. Now you see that the space station is incredibly big. They always ask me, do you feel claustrophobic? No, I don't, because it's really big. It's as big as an airplane, so it's not like living inside a submarine. This is a warehouse, and also we have such freedom. This is Karen pushing herself with just one piece of hair. See how easy it is. It's an experiment that I couldn't do, obviously, but Karen could. And talking about future, this is something. What we are doing here is also part of the future. We use our equipment in extreme environments. So here, we are in Columbus, the European lab. This is a rack, and I'm repairing a piece of equipment down here. And when I say that we are testing the future, well, we have to know, if we want to go to Mars, and it takes us, right now, it would take us 6 months to fly to Mars. We have to know how long, go ahead and pause it. We have to know how long our equipment can last before we have to change it. Because guess what? If you are on your way to Mars, there is no way to send a piece of equipment back from the Earth. Either you built it on the station, and right now, talking about future, we have 3D printers in orbit with which we are printing small pieces of equipment that we can use to replace failed tubing, failed piping, small parts that are easy enough to repair and don't need strong structural parts. But it's plastic that's being printed on the space station. It's amazing. That's the future. Another thing that I'd like to talk about is this piece of equipment here. And it's the third time this week that I talk about it, because it's incredibly important. It is a mix of past, present, and future. This is the toilet. So, since it's just a container, I would say that that's the past. Even if you showed an Egyptian from 3,000 years ago a container and said, this is your toilet, he would probably recognize it. However, it's something universal. We humans have a feces, we have urine, and we have to find a way to get rid of it. And this is very basic. We just put it in a container and leave it there. However, I promise you the future. And the future is right here. This is a mix of present and future, as a matter of fact. This is a filter. Chris Cassidy here, my crewmate, is replacing a filter for what we call the WPA, the water process assembly, which also contains the UPA, the urine processing assembly. Those two things are connected, because what we do is we drink the coffee in the morning, which is brown. It goes through our body, becomes yellow. Then it goes through this whole system, and these filters, it turns transparent again, and a week later we drink it. Now, if you go into Mars, and it takes you 6 months, there is no way you can take all the water you need. It's impossible. Water is heavy, it's very dense. 1 liter of water is 1 kilo. And weight is so important to minimize. So I can guarantee you, where is my astronaut? I can guarantee you that when you fly to Mars 20 years from now, with much shorter hair, you will be drinking not only your urine, but everybody else's urine. And it will be something possible. You're drinking dinosaurs' urine anyway on the Earth, so it's nothing different. But you will be using something very similar to this, only possibly much smaller and much more efficient, because right now we are still not recycling 100% of what we drink. We still have to eliminate something. And also, more likely than not, I hope, you will be using whatever is left in this container. You will probably be using it to grow food, hopefully. We are researching, talking about research in future. We are studying now on the ground. There's a site in Spain that belongs to ESA, and other places in other institutes. We are trying to find a way to create a closed system where we can recycle everything. And that will be the future. It's the only way that we can imagine landing on a new planet, whether it's the moon, or which is not a planet, to land on a new cosmic object, whether it's a moon, whether it's a planet or an asteroid, as ugly as they are. It's the only way we can imagine to land there and terraform the surface, make it livable for the humans. We have to have a closed environment. So our water will be recycled, our air will be recycled, our feces, our organic waste will be recycled. Go ahead and start again. So this is where science and technology meet together with our needs. This is part of the Russian system. Karen here is showing you her room. So we don't have a lot of space in space. Our rooms are as big as a telephone booth, for those of you who remember what a telephone booth looks like. Not many. Now, pause it for a second. Okay, we were talking about research and future. This image behind me, this very short video, showed you a burner. It's a combustion chamber that we have on the space station in the US lab. And it's an amazing piece of equipment because you can imagine that space stations and fire do not go well together. It happened once in the Mir. It didn't go too well. So we don't want to recreate a fire on the space station. However, we have experiments right now that use this combustion chamber to burn. And what do we burn? Well, we burn all kinds of things. We love burning things. We have to be a bit crazy, but we really like to burn things. So we burn different kind of material to see how they react in burning in zero gravity. And that's an unfortunate experiment that I couldn't do. However, this was part of one of the experiments that we did while I was on the space station. Here, in this experiment by the Italian Space Agency called Green Air, we are burning biofuels. So these are organic fuel created on the ground, not fossil fuel, but biologically. And the experiment was to find a combination that would create the least amount of toxic waste. Now, when we burn something, we always create something toxic at the end. It's inevitable. It's the nature of combustion. But thinking about the future, again, your future, your hands, your time, thinking about that, we want to imagine a future where biofuels that we can recreate without wasting them, leave the air a little bit cleaner, have a less of an imprint that we are doing now. So this is the beginning of that voyage. It's the beginning of that capability, but it starts on the space station. And you may ask me, why don't we do it on the ground? Why do we do it on the space station? Well, we noticed that in orbit, in a zero gravity environment, the shape of the flame and also the combustion itself is a little easier to study. We have less dimensions. We take one dimension away, the gravity. And so it's easier to study, and the results are easier to compute. Now, I don't have the results of that experiment because it only happened 1.5 years ago, and science takes its time. But we're talking about the future here, so I thought that was a good subject. Go ahead. So this is actually an experiment where we're burning some kind of material. Talking about future, how many of you like robotics? Where are my engineers? No nerds? No? So robotics is very big in space because we always think about movies like 2001 Space Odyssey, where HAL killed everybody on orbit. And so we are studying the ways to use robots to do our job. So Robonaut is a very dexterous robot that can help us doing EVA. And these two spheres, it's an experiment called Spheres. Go ahead and pause it. That's an interesting story. So how many of you have watched Star Wars? Good. That's the kind of answer that I like. So in the first episode of Star Wars, the original one, in the original Star Wars, Luke Skywalker meets Yoda, and then he trains to become a Jedi. He's got a sword, he's blindfolded, and there's a little robot shooting lasers. Remember that scene? Good. So a professor of MIT that was just as much a fan of Star Wars as I am, asked his students to build the robot. And the result is the program, the Spheres program nowadays. And there's going to be soon another one that is even more improved. Now, Spheres, those little robots have an artificial intelligence, not too bright. They maneuver in space in 3 dimensions, and we use them for competitions with students where we ask them to create maneuvers on the ground for them to see which kind of maneuver in 3D is more efficient. So we've had also some other experiments where we try to see how we can, for example, navigate in 3 dimensions for example, to inspect something outside. Because in case a communication antenna breaks, you don't want to send an astronaut and then lose him in space. Just kind of kind of like a space odyssey. Here's another piece of experiment that's really interesting. In space, because we are free from the gravitational effects, we are still under gravity. Gravity is a universal force, but because we are continuously falling, we are free from gravitational effects. Liquids behave in a very interesting way. They become spheres, and you can also, by changing the shape of the container, you can create movement. So this experiment, which is an experiment on capillarity, which continues until today, deals with that. The capillarity, changing the shape of a container, creates a motion. So imagine if in the future we can have pumps moving liquids from one place to another without using energy. It's a pretty clever way to do things, in my opinion. Go ahead. Yeah, it's not moving really fast, but it's moving. That also matters. Talking about future, here is another part of the science that we do on the space station that concerns future. Here, Karen Nyberg is taking an ultrasound of the spine of Chris Cassidy. Now, until we did this experiment in orbit, we didn't think it was possible to actually get a good image of the spine, but we did. And the image that you saw after that was an ultrasound of the ocular bulb. This is to study. Go ahead and pause it. I promise I'm gonna make it faster from now on. But this is it's really the meat of what we do on the space station. It's the study of the physiology. When our friend wants to go to Mars 20 years from now, we are going to have to find a way to prevent his body from degrading, from degenerating. And that's what we're doing on the space station now. We are using our body as testing equipment. We are letting our body degenerate at a faster rate than here on Earth, so that you can go to Mars 20 years from now and get there and land once, not 3 times, and land and still have strong bones, strong muscles, and good eyes. Because right now, when we go in space, if we don't do anything, we come back and we would have a very damaged body. But we've done a lot of research on that, and so we are getting much better, so that in the future we'll be even more capable upon landing. Go ahead. Yeah, not a very clever face in this image. I'm just happy because I'm preparing for an EVA. So what we're seeing here, this is a cable. It's called safety tether. It's a metallic cable that we use on orbit in order to attach ourselves to the space station when we do an EVA. Now, why is that important? Well, it's very important if you've seen the movie Gravity to prevent that from happening. We don't want to get lost in space, because if we do, it's a very bad day, incredibly bad day. So we have a safety tether, kind of like a dog on a leash, so that we would come back to the space station in case something happened. Now, this part of the video is one of my favorite, because even though the spacesuit are certainly not the same spacesuit that you see in the movie The Martian or other sci-fi, these are the suits that we're using now to perform EVAs. And EVAs are amazing. They're fantastic. You go outside in the most dangerous place in the world or out of the world and work. Now, if this is not science fiction, I don't know what is. It's beyond my dreams. And it was amazing to be part of that. This is me coming out in my big Michelin Man suit. And once again, this is part of the future, because when we go to Mars or when we go back to the moon, we will be using something that is going to look very close to this. Hopefully it will be an evolution, but it will be very similar. And we are testing these suits to their limits, because nowadays these suits were created to go to space, perform an EVA, come back to Earth and be refurbished. And we are not doing that. We are pretending that we are on our trip to Mars, and we leave them on the space station, and we refurbish them as much as we can on the space station. And sometimes they fail. So for example, on my second EVA, there I am. On my second EVA, something went wrong. And just as I was saying earlier, when something goes wrong during an extravehicular activity, it's a very bad day. So this is me on my first EVA. You see this backpack. This is the tip of the space station. We're flying at 28,000 an hour in this direction. The backpack is called in English a PLIS, Portable Life Support System. It generates an atmosphere. Can you pause it? Okay, it generates an atmosphere inside the suit. It creates a ventilation so that we can breathe. It also circulates water for a suit that we wear underneath the suit with lots of little tubes, kilometers of little tubes, to drain the heat out of our body. So, who has seen the movie Gravity? Yeah, okay. So when Sandra Bullock takes off the suit and she's wearing hot pants, that's not accurate. So instead, we have this suit with water circulation. And that day, the system that is in the backpack, there is a pump, a very tiny pump that creates this motion of air and water. That pump failed. And instead of separating the water from the air and generating ventilation in my helmet, it started spraying water inside my helmet. And that's what the simulation is showing, the way the water was flowing over my noggin. Now, on that day, probably if I had hair like your colleague, it would have been much better. But I don't, and so water was flowing over my head, and then go ahead and start it again. And until it started covering my eyes, my ears, and my nose. So I was outside of the space station, completely isolated, and I couldn't see, I couldn't speak, and I couldn't hear. I couldn't really breathe, but only through my mouth, and the water was filling up my helmet. So, yeah, it was a bad day. However, going back, this is the part where they tell me to go back inside. I'm going back inside here, inside the hatch, trying to, this is doing the repressurization, and this is the moment when they bring me inside. Here I am, just like a sack of potatoes, and my helmet is half filled with water. Look at the faces on my crewmates. They were not happy. And then finally, look at all the water flying around. That's water that was attached to my noggin, and this is the effect of the water. You see why I was saying that if I had hair, probably the problem would never have started. But instead, because water becomes like a gelatin, and it stays. Go ahead and stop it. And it stays attached to the skin. My daughters loved it when I showed them this trick on the space station. Every time I had a video conference with my daughters, they say, "Do the water thing with your hair." And I'm like, "Okay," and I would do the water, spray the water, and then shake my head a little bit, and they called it the water hair. So they're young. So what can I do? What can a father do? So it was a very bad day for me. However, when you go back to that event and translate it into the future, and that's what we're talking about tonight, everything changes, and it was a great day. It was a very good day for space and research for three very good reasons. The first reason, my favorite one, is that today I'm here talking about it. So it was a good day because I'm, at least for me. I have to ask my wife about that, but at least for me it was a very good day. The second reason is that the most important is that we found a problem that we didn't think was possible. And that's, again, the same reason why we use those old-looking machines and we use old-looking spacesuits. Well, because we like to know. We don't like surprises. We like to know what kind of problems we can have. And we try to think in advance. But even the best engineer in the world cannot think of something that we have never experienced. We can think of accidents that have happened on other systems that are similar. We can think of airplanes, we can think of cars, trains, we can think of underwater suits, but we cannot think of something that we don't know. So when we built the spacesuits, we didn't think that this accident was possible. We thought that the water would just flow away around the helmet. It would be uncomfortable, but not dangerous. We never thought that it would accumulate in the helmet, covering the head of the astronaut. So that day, we discovered that it's possible. And I can guarantee you that it's never going to happen again, ever. Because now we have systems in place that will prevent that from happening. We have also, in case that system doesn't work, we have a backup system we have a snorkel that goes inside the suit so that an astronaut can actually breathe from the rest of the suit while the other person brings him inside. But most importantly, we have found a problem that will never happen in the generation of the future. Because right now we are building new spacesuits, and they will be different. They will have other problems, but they will not have this problem. And so we already made a step in the future when my accident happened. And the third reason why it was a good day that day is because we discovered that our training works. Because even though we didn't think that was possible, there was no procedure for this kind of emergency. There was nothing that I could read or nothing they could tell me to do. Well, our training worked anyway because they prepared me for all kinds of evenience. And so when I found myself isolated and blinded, I was still able to navigate just remembering the structure of the space station after hours and hours and hours, hundreds of hours underwater. I have over 180 hours underwater in a spacesuit identical to that, navigating around the spacecraft. So with my eyes closed, I knew where to put my hands so that I could go back, even in the most dire situations. So, a good day after all. Go ahead and start again. I'm going to try to make it fast, but here is a piece of past that transforms into the future. I like this comparison. This is the ATV, Automated Transfer Vehicle, an amazing machine built in Europe. And it's built in Europe, it's a European technology. Actually, the pressurized module is Italian technology, it's built in Italy. And it's a program that's completed, it doesn't fly anymore. However, the basics of the program will be the service module of the Orion spacecraft. For those of you that know what Orion is, the service module comes directly from there. This is another spacecraft. It's called HTV from Japan, obviously. The Japanese name is Kunotori, which means the white stork. And it's a different technology. While ATV is automated, meaning it docks by itself. And after traveling for millions of kilometers, it docks with the precision of 1 centimeter. So a lot better than 100 meters. So we beat you again. But this spacecraft and the Kunotori, they work differently. They park themselves at 10 meters from the space station, and then we capture them using the robotic arm right there. This is the robotic arm flown from inside, and that was me actually flying the robotic arm when we capture Cygnus. And this is basically how we inside we bring all the food, our clothes, and then after we empty it out, we fill it up with everything that we have to trash, and we make the most beautiful comet. No, it's more like a shooting star. It's a shooting star made with our trash, and then we burn it in the atmosphere. We atomize it. Now, this is a little slideshow of views that we have from the Earth. And here there's 2 words I'd like to say, my 2 euro cents of wisdom about these views. This is the present. This is not the future. However, I would like the future to be very similar to what we're seeing now, if not better. And the world that we live in is just like the future. It doesn't belong to you, but it is in your hands. So it's up to us to keep it going. Now, a little lighter theme here. This is me playing completely alone because nobody likes my music. Karen in the earlier picture was washing her hair. This is me playing the guitar, again, completely alone. This is the look on Karen's face while I'm playing the guitar. On the space station, we are humans. We have to have our downtime, and so we do what we can. While I was playing the guitar, we play with fruit. We eat. These are scrambled eggs, and you have to know that they're scrambled eggs because we don't know that they're scrambled eggs. They have to write it here, so that we know what we're eating. How is this connected to the future? Well, hopefully, this is not the future, but the food of the future in space is gonna have to be something very similar, because again, these are strawberries that have been rehydrated with a dry biscuit and some milk rehydrated, and we call that strawberry shortcake. the food is incredibly important. And so to develop food in the future that will be more appetizing and with the right balance of flavor and taste and look is extremely important. And again, for our friends that wants to be an astronaut and go to Mars, these machines are what we use in orbit to keep our muscles working, our heart strong, and our bones in good shape. So those are the evolution of those machines. These are already very much more evolved than what we used at the beginning. The evolution of those machines is what we will use in the future when we go visit our planets. Well, this is the moment of the goodbye, so I bet you guys are all like, oh, finally, this guy's going to stop. Well, for me, it was a very sad day. This is Oleg, our commander, and this is the moment where my spacecraft detaches itself from the space station. We are inside our little spacecraft. We are inside here. And now the sky, when we look outside, is all black, completely black. When we slow down by 128 meters per second, from 8,000 meters per second, the sky becomes white. This is plasma. These are parts of the spacecraft that are burning and fly at Mach 25 next to the window. It's amazing. It's 1,500 degrees outside, about 50 degrees inside. And it's so hot that even though we have ventilation inside the spacesuit, we are still sweating in buckets. So if there is one thing I like to say about the future is that I hope that spacecraft get better, because what we have now is small, uncomfortable, incredibly hot. But it works. Again, old systems that have been tested for years and years. When the parachute opens, we are happy as kids. We were laughing and hooting and cheering until this moment. That is the soft landing, and just like Philae, we did 3. So we landed, and then we bounced, and then we bounced again, and then we found ourselves on our side, and this is the moment where they finally take us out. When they first opened the window, the port, I was hoping to get a nice fresh breeze of air from the earth, maybe the smell of the grass. Unfortunately, all I got was the smell of gasoline being burned because there was a little fire outside caused by our engines. But you cannot have everything. We were alive, we were happy, and we had the Olympic torch with us, which apparently was more important than the crew, because first they extracted the commander, then they extracted the Olympic torch, and then they extracted Karen, and then they came for me and they said, Luca, you're way too big. We cannot take you out, so you have to take yourself out. And it was incredibly, see all the sweat? I'm completely drenched because pulling myself out of the spacecraft was the hardest thing I've ever done other than the Ironman, and just about as fatiguing. And then this is the moment where we fly back, and it's not really the end, because after about 21 hours from Kazakhstan, we land in Houston. When we arrive in Houston, we just get a little peck on the cheek by our friends and family, and then we are thrown right away into more experiments. They prod us, they take biopsies from our calves, they shock us with electricity. I'm not kidding. These are all actual experiments. They take our blood, our urines, and then for days and days and days and weeks, which turn into months. And all of this is for the future, because we have to figure out what happens. I have a big head in that video. We have to figure out what happens what happens to our body before the flight, during the flight, and after the flight, and how long does it take to go back to where we were. So that science is incredibly important. It's not the end of the flight, it's just the beginning of a new phase. And the new phase also includes what we're doing here tonight. It is to talk to you. It is to tell you why it is so important to work in the environmental research, why it is so important to go look for comets, why it is so important to go from the incredibly big, from the beauty of space, of galaxies, of the unimaginable, to the infinitely small of the Large Hadron Collider. All of this is part of what we're doing now to understand where we are, but really what's more important is to see where we're going. And only you will have the answer to the question. Thank you for your attention. I'm ready for your answer.